All right, in this video, we're going to design our own potential energy level diagram with some numbers given to us and a reaction given to us. So it is long sometimes when you're reading these questions. There are longer paragraphs, but don't be too concerned. If you take it step by step, it's going to be pretty straightforward for you to do. So carbon dioxide reacts with nitrogen monoxide. So I'm just going to write that out here this is our reaction. We have carbon dioxide reacts with nitrogen monoxide, NO gas, to produce so carbon dioxide and nitrogen monoxide. They're going to produce carbon monoxide, so CO gas, plus nitrogen dioxide, NO2 gas. So that's our reaction that we're dealing with. We want to draw a potential energy diagram to illustrate the progress of this reaction. You don't have to draw it to scale. You're just going to have to make sure you have the proper numbers there and things in the right position. So I'm going to start off by drawing the skeleton to my potential energy diagram, just drawing a little graph like this, a graph like this. And I'm going to label the axes at the very least. So here I have potential energy, PE, and that's going to be in kilojoules. So in kilojoules, like that, okay? And on the x-axis, I'm going to have the reaction progress. In other words, this is my forward going left to right. So forward reaction. So I'll start with that at the very least. And now I'm going to try to place my reactants and products. So to do that, I want to take a look at my delta H. You'll notice my delta H over here is positive 226. So what that means is that my product should be higher in energy than my reactants are because there was an absorption. So that makes it nice and easy for me. I'm just going to draw a line to represent my reactants. So I'll have the CO2 plus the NO. And then a little bit more to the right, I'm going to draw a line to show my products are higher up. It doesn't really matter how much higher up they are, just higher up in general. And so this will be my CO plus NO2. And what I'm going to do next is I'm going to draw a little curve to show that there was an activation energy barrier. And then I'm going to make it at the end essentially start going up. And then once it reaches a peak, it's going to start going down to the product. So we'll go something like this. Like that there. Okay. And so what I did here is I drew essentially the highest energy state. This would be our transition state with our activated complex. And so we can label a couple things now. We know that the delta H of the reaction is positive 226. So I'm going to go ahead and label that in blue over here. It's just the difference in energy between my reactants and my products. So I'm just going to make a little line here to show that we're not going all the way down to the graph. We're really going between reactants and products. So this is going to be it over here. This is our delta H. So this is our delta H, and it's larger than 0, making that an endothermic reaction. We are also told our EA of the forward reaction. So let's label that one in green. So EA of the forward reaction is from your reactants all the way up to the highest point, all the way up to the transition point. So this is EA forward. So that's the EA forward. So that's the energy required to be added to our reactants in order for the reaction to actually occur when there's effective collisions, for effective collisions to actually occur. So there's our EA forward. So we could let me just label the EA. So this is equal to positive 361 kilojoules, kilojoules. Whereas the delta H we said was, so delta H is equal to positive 226, like that. So that is our delta H there, and that's in kilojoules as well. So we've labeled a big chunk of our diagram so far. We still have one more thing to do. We want to calculate the activation energy of the reverse reaction. So that's what the question's asking. That's how I know I want to do that. So here is we want to EA reverse. In other words, if our reaction was going in the other direction, if our reaction was going from right to left, what would the EA be? So your products are sort of the new reactants in this situation here. So what we're going to be doing is we're going to be doing the energy all the way from what were the products all the way up to the highest point. So I'm just going to make a little dotted line here just to show where the highest point was. And this will be our EA reverse. EA reverse. That there. Now, for the EA reverse, we want to calculate it. We want to see what it actually is. So remember that there's a relationship that exists here. We know that the EA forward minus EA reverse is equal to your delta H. So what that means is that our EA reverse, if I rearrange everything properly, is going to be, so if I send this to this side and this to this side, it's going to be EA forward minus delta H, In other words, it's going to be the 361 minus the 226. So if you do your 361 minus 226, you get positive 339 kilojoules. So your EA reverse is a little bit less than your EA4. Actually, I don't think I did that right. My math is off there. That's why I was confused. I used a calculator too, and my calculator just didn't work because I punched in the numbers wrong. So always kind of question yourself before you're about to put a final answer down. How could I subtract 200 and still be in the 300s? Doesn't make sense. So 361 minus 226. There we go. This one makes more sense. Positive 135 kilojoules. So the EA reverse is positive 135 kilojoules. So a lower EA than the EA4 in this situation. So let's just make sure we have everything. Let's double check everything here. So we had labels of the y-axis with units, label on the x-axis. We have our reactant identified, our products identified. We labeled our delta H with the value given to us. We labeled our EA forward with the value given to us. We labeled a transition state and activation complex. We also found our EA reverse. And we found the actual number using the relationship that we described in a previous video over here. And that's essentially all that the question is asking. So if you got to this point, that means you understand the potential energy level diagrams quite well. Now you're ready to try practice problems here. You can find a link to the worked solutions for these problems here as well. You don't have to do every single question, but do them until you understand the concept well. If I were you, I would redo all the problems and notes within the actual note first, and then you can go on to do these practice problems here.